Okay, so what we are going to do is to talk about something more relevant. Okay, I know in this room not many of you will be interested in improving that result. I want to talk about backpropagation because I guess many of you have encountered this term before, but you may not be able to really understand what is going on in the backpropagation algorithm. So, and this is just a slide summarizing of what you will encounter on the internet. What I'm going to do is to follow a book. This is an online book by this gentleman, Mike Nelson. So what he has is a set of equations. Okay, very, very simple equations, but it's so simple that you can understand. Okay. Now, if you read other lecture slides, they will just tell you backpropagation. It will be they draw some graphs, and then they have a bunch of numbers, and then they add things up, and then you don't really know what the numbers are meaning. So I'm going to follow this book. Now, I'm going to summarize the most interesting parts of the book. You are more encouraged to read the entire text because he has more explanations. He has some really, really interesting illustrations on his book. Okay, so let's look at the problem. What is the problem? Well, the problem is you want to learn the wave matrix, and remember that you have a sequence of wave matrix, and then you have all these nonlinear activations. It has to be there because there's a steep neural network. So we want to be general enough to handle all these together. Okay, so if this is the loss function, how are you going to do? Well, you say, I'm going to run gradient descent, and by gradient descent, you're going to take the derivative with respect to each of these, and then you make a step towards that direction. So in other words, if I'm going to update W1, I'm going to take the derivative with respect to W1 and then make a gradient descent update for W1. And similarly for W2, etc., etc. So if you want to do this, you need to do for all these together. And that could be a disaster because it's all lumped together. How can you do the gradient descent for one by the other? And the answer is, if you do it carefully, even by brute force, you'll be able to get the gradient descent to work. And this is backpropagation. Now, you think that backpropagation is so mysterious, and it's actually not that mysterious. It's brute force gradient descent with very careful bookkeeping. So let me illustrate what's going on. Let's assume that you only have 2 layers. That's simple enough. 2 layers. You want to update your W1 and W2. How about we update the W2 first? So that means I'm going to take the gradient of my loss function with respect to W2 and then make an update. So you take a gradient step of W2. How can you take the gradient step of W2? It's not too hard. I can just call this gentleman as A2. Okay, it's just something. I am going to take the derivative of J with respect to this A2, and then I'm going to take the derivative of A2 with respect to W2. Right? Okay, now you say, how complicated can this be? This just chain rule. Okay, and so now the only thing you need to worry about is how are you going to handle this nonlinear activation. But if it is sigmoid function, we know how to derive the derivative of a sigmoid function. Okay, so in the logistic regression case. So we know how to take the derivative. And how about the inner one? Well, the inner one actually doesn't really matter. It's just a vector. It has nothing to do with the W2. It's a vector. And so taking the derivative of A2 with respect to W2 is doable. Okay, just need to be very careful, sit down, be patient. You should be able to get this derivative. In the same principle, you should be able to get that. And if you do it carefully, don't make a mistake, you should be able to get the gradient of J with respect to W2. Here is what you do, okay? And just take this chain rule here, and then calculate each individual elements, and then you get the gradient, and then make an update. How do you do a W1? Same principle. You call the inner guy as A1, outer guy as A2, and then you want to take the derivative with respect to W1. So you take the first chain rule with respect to A2, and then take the chain rule with respect to W1. But this guy is a little bit complicated because it includes another layer. And so you do one more chain rule, taking it with respect to A1 and then W1. And so you have a sequence of A2 to A1, A1 to Z1, Z1 to W1. What is Z? Z1 is just W1X. Is it complicated? It's just tedious. Okay? All right? So just follow this chain rule to the brute force. You get a sequence of derivatives. If you calculate them correctly, multiply them, you get the gradient, and then you make a gradient descent update. That's backpropagation. Is that clear? All right? Okay. So now, of course, the invention is not at this point because this anyone can do. The credit goes to the authors because they have a little bit more careful way, systematic way of doing these without going into the tedious details. So I'm going to introduce a set of notations, okay, and then I'm going to introduce a set of equations, and then by following the notations and also the equations, you can derive a set of algorithm. Okay, so that would be the flow. Okay, notations and then equations, and then we will look at the algorithms. Okay, so assume that you have 3 layers, and then you have several number of nodes in each layer. I am going to call, using the notation I introduced before, this 3-index notation. Okay, so this is one example. So you have a weight, okay, at the 3rd layer, okay, W3, the 3rd layer, you are going from node number 4, so this is the entrance, 4 to 2. Okay, 4 to 2, so you have 2 and 4 here. Now you wonder, why don't you just flip it over? Or it's because it's backpropagation, so you're going from the backward, and so from the backward is 2 to 2, and then coming from 4. That's just the culture, okay? Historical reasons that you want to do backpropagation, so the index going to the other way. So that is the index of the weight. That's fine. I am also going to define the values, okay? I call them the activation, you call them the values or bias, just some numbers. They are the numbers living on each node. What I mean is that at each node there will be a value. This one, it says that A31, it will be the 3rd layer. The first node, you will have a number. And at every node, of course, there's also a bias, okay? And then the bias will just be the offset that you add to that layer. So if you look at this equation here, you have W transpose X plus W0. This is our linear discriminant function. If you are patient enough to write them out, okay, then you have a summation of all the W, I, J, K, L's, and then times the A, K, L minus 1. Well, because you're propagating from the 2nd layer to the 3rd layer, and so the value that you're obtaining at this point would be the sum of all these nodes added together by these weights, and then you plus an offset. Correct? Okay? And so that would be the value that you're gonna get. This is like a forward pass. Okay? I'm not talking about backward yet. It's just the forward. This is how you can get the forward values. Okay. Now, to understand this backpropagation, we need to identify a few like a stack of like a hierarchy of variables. So remember when I introduced this 2-layer problem, I actually define something in the middle. I say that, okay, I'm going to take chain rule with respect to that thing first before I take the chain rule of the other layer. So now what is that? Well, I'm defining a thing called the Z. Okay? Z is something inside your activation function. Now, because why do you want to do that? Because you want to first take the derivative of that activation function first. Okay, so that's the logistic function. And we say that, okay, logistic, it will be a logistic function times the 1 minus the logistic. So that would be the derivative. This is the derivative of that function. And inside that function, you have a quantity, and then you want to take the derivative of that quantity. Okay, is it complicated? It's just tedious. Okay, bear with me. Be patient. Okay, follow this line of thinking. Keep the book carefully, and then you will understand. Okay, so you have a logistic function, and then you have a intermediate variable. I define it as z. Then your a, the same sigma, and you just replace whatever inside by z. So that is the expression you're getting here. So in terms of this diagram, you can see that if I have a forward pass, I have these values, adding them together, and that will give you a intermediate variable. After the nonlinear activation, you get your response. So now we can talk about backpropagation. How do we go backward? To go backward, you need to start with the terminal. What is the terminal? The terminal is the loss function. Okay, it is the loss because you want to backpropagate your loss and the error back to the beginning, and then your forward pass, and then going back. So what is the loss? The loss here is defined as C. In our case, it would just be the square loss. Now you can choose other loss. That's also equally fine. This loss, in this case, it would just be a square loss and you sum all the possible nodes. Okay, so that would be L. This capital L stands for the last layer. Okay, and then this 1 stands for the first node of the last layer. Y1 would be the label of the label. So suppose that your label vector is a vector, okay, and then it has multiple elements. So that will give you Y1 and Y2. This is your loss. And then what you are going to do is that you are going to define the error. Okay, here is your loss, and then I want to define the error as the rate of change of my cost as a function of all the intermediate variables z. So this will tell you if I make a small perturbation in my z, how much cost it will be changed. Okay, small perturbation. Okay, now you can show the following. You can show that this error, okay, the error is defined as the partial derivative of your loss with respect to this z. Okay, so that's the definition. Don't argue with me. That's just the loss. And you can show what? Well, you can show that the loss, that this delta, this error, can be written as this delta c, partial c and partial a times partial a and partial z. Isn't it complicated? No, it's just chain rule. Why? Well, think about this. You have all these neurons, and then there is an activation, and then that will go to your c. So what you're doing here is that you're going to take the partial derivative with respect to your activation first, and then go inward to take the derivative with respect to your z. Okay? So it's just chain rule. And now if you write it out, this is just the what? Well, that's just the derivative of your activation function, and this is your cost, taking the rate of change of the cost with respect to your a. Okay? So this will give you one equation, which will become very, very useful, because once you have this error term here, what we are going to do is that we are going to go backward one layer by one layer. And if we can set up that sequence of propagation, then we have completed our goal of backpropagating the error. Okay, so this is a very, very important equation that defines the error as the derivative of c with respect to z. And then, according to chain rule, you can write it this way. Okay, so this is, I call them the 4 fundamental equations of backpropagation. Similar to Maxwell equation, 4 equations for Maxwell, okay? So 4 fundamental equations for backpropagation. This is the first one. It is the error of the output layer. Just remember that now, you need to start your backpropagation from somewhere. It has to start from the output, and so you need to define the error from the output. That will be the first equation. Okay, so now, we are going to write very compactly about this equation. How are we going to write that? Well, we are going to write in this way. This is a vector notation. It's not too complicated. It's just a shorthand notation That takes people several days to think about that. It's not hard. You have this vector of z, okay? And then each of these elements, you pass through an activation function's derivative. You can calculate that. It's logistic. You have a lookup table. You can calculate this easily, okay? So it would be an element-wise derivative of the z's. This one is nothing, but it's just the gradient of your loss function. And then it will give you a vector because you're taking the gradient with respect to all these aj's. Okay, so that would be the gradient of c with respect to a. This circle dot is just called the element-wise multiplication. In MATLAB, it's dot times. Okay, dot times. Is it okay? All right. So this says that if I have a loss function here, this is my c, and then I have a bunch of a's, then the error that I am going to get at these stages will be defined by this number. Okay, it will be a vector of numbers. And if you choose the L2 loss, then all these are pretty easy to calculate because this gradient c is just the 2 norm square, right? 2 norm square is just one of those. And then the derivative, you can pre-calculate them. So this should be easy in principle. In terms of calculation, it is not too complicated. All right, first equation that defines the error at the output. Okay, I haven't propagated yet, okay, but I have defined the error at the output. The second equation is very, very important. The second equation tells you how are you going to propagate the error from the end to one layer before that. Okay, this equation is given by this. You have the delta L on the left-hand side, and on the right-hand side, you have a delta of L plus 1. Okay, so this, because it's bare propagation, you have to start with L plus 1, and then you go to L. If you start with L, you will go to L minus 1. Okay, so that's the bare propagation. In this bare propagation procedure, you can see that I am going to multiply my error by the W's. Why is that? Now, you can prove that. It will take you some pages, but we can just prove by picture. Go to here, you have all these error. This is delta 1, delta 2 at layer L, at layer L. This is the output. And then you look at the graph. The graph will give you the edges. You ask, what is the error that I will see at this node? Well, frankly, you just multiply the error with this way, and then the error with this way, add them together, that would be the error. Okay? And now, when you go to this error, it's not just the error, because it would be before the activation. And so you also need to do one more step of after the activation. And what is it? Dot times your activation derivative. Okay? All right? Isn't it clear enough? Okay? So you take the error at the back, propagate one layer before, and then the propagation is done by multiplying the weight. Okay, so that's equation number 2. And then equation number 3 and equation number 4, they are what? Well, they are telling you what is the gradient that you care about. Now, what do I mean? Well, the gradient that you care about would be the gradient with respect to your weight and the gradient with respect to your bias. And how are they defined? Equation 3 and equation 4, they define the gradient. With respect to the bias, it would be just the error. With respect to the weight, it would be your activation times the error. Okay, that's also not too difficult to prove. Okay, if you sit down, you're patient enough, write down the chain rule, you will get to these 2 equations. Okay, so these are the definition of your actual gradients that you want. Okay, so 4 equations: destination, backpropagation, and then defining the actual gradients for your gradient descent update steps. 4 equations. Okay, now after these 4 equations, we will land onto an algorithm. Look at this algorithm. It's very, very simple. This algorithm says that I am going to initialize your X and also the A1s, and then I'm going to do a forward pass. Because why? Because remember in equation 2, you need to have all these W's ready. How are you going to get all the W's ready? You need to do a forward pass, calculate all the W's. Once you calculate that, then you can start to do your favorite backpropagation one step at a time by doing all these errors and then propagating one by one by one until the end. Okay? When you go to layer 1, forward pass again, update all the W's, and then go back. And so how are you going to update the W's? Well, updating the W's, they are given by the third and the fourth equation. How are you going to backpropagate? The backpropagation is given by the first and the second equation. Okay, so now you have forward and backward all defined. Okay, so just a few more pictures to illustrate this idea. So if you look at this algorithm, you have multiple steps. So the forward step is that you start with all these A's and then you multiply them together, you form a forward pass. Okay, so that would be forward movement. If you are at the end of your network and then you want to go backward, that will go to equation number 1. That defines the error at the output layer. And then as you try to propagate, then you use equation 2. You take all these ways and then take all these errors, you go backward. Okay, that is backpropagation. Okay, I hope I have demystified this backpropagation. Is nothing too complicated. It's just a sequence of chain rules that you need to be very, very careful. Okay, so you can read the slide about the summary of the backpropagations. Okay, so this is a very interesting paragraph I found from Nelson's book, where he says that how did the people first invent backpropagation? They really just sit down and write out all these complicated, tedious chain rules, and then they make simplification, 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 until the end, it becomes so clean that you lost the intuition. Okay, and that is the final algorithm. But if you want to prove it back, you just go from the beginning and do all these chain rules. All right, so here is the reading list. I highly recommend you to take a look at this online book, chapter 2. It's very, very well written. You are also encouraged to read this textbook, chapter 5. It's a little bit more classical treatment, but it's also comprehensive. The Chris Bishop's book is somewhat more for Bayesian. If you're Bayesian statisticians, you may not like that. The Stanford CS231 lecture slides, they have some very good numerical examples, but they do not have this kind of the 4 fundamental equations to help you understand the intuition. So when you try to read them, treat it as like a very good reference, okay? And then refer back to the equations that we're introducing in this class. And in 2 other schools, they also have similar discussions of this backpropagation. And so take a look and make sure that you know what is backpropagation before you click a button and call it in the library. All right? Okay, so we will resume our class next lecture.